stats lesson for the week. This week we're learning about ANOVAs, or analysis of variance. ANOVA is very similar to a t-test, only you'll remember with t-tests we could only compare two groups, where in ANOVA we can compare two or more groups. So to practice ANOVA this week, we're going to run a set of data with 3 breeds of cattle, and a measurement for rib area in square inches, and a measurement for weight gain. For the purposes of this example, we're just going to run the data on weight gain. So I'm going to go ahead and delete the data for rib area. And so I have 2 columns right now, breed and weight gain during our feeding trial. In order to run an ANOVA in Excel requires that the data is side by side in columns. And so first thing, we need to structure our data in a format that Excel likes. So I'm going to add a column at the top, or a row at the top, and I'm going to label the first one Angus. Then I'm going to go down and copy the next breed worth of data. And I see that's Charolais. I'm going to do Control-Shift-Down arrow to copy the data, or to move down to the bottom of the data, copy it, then I'm going to paste it up there. Label the next one Charolais. And then I'll go down the bottom of Charolais data and find the Herefords. Cut them and paste them up here. And then we can go through and delete the extra columns. Then you'll see I have 3 columns of data, each labeled with the breed side by side. Also, want to double check that I deleted all the extra data, and I have 105 cattle of each breed. The next step in running an ANOVA is to always do descriptives, just so you can see what's going on in your data. So to do that, I'm going to do the Data tab, Data Analysis, and then do the Descriptive Statistics option. Now from input range, I'm going to highlight my data and do Control-Shift-Down arrow again to highlight all my data. I'm grouped by columns. I do have labels in first row. My output range, I want it to be something like E2, top of my page. And then I want summary statistics. So I check that box and click OK. And in this box, you'll see we have each breed, Angus, Charolais, and Hereford. And then we have the basic summary statistics for mean, standard deviation, median, mode. And from this, I can see that the mean for Angus is higher than the mean for Charolais and Hereford. But we don't know if that's statistically different or just a matter of random chance. So we need to run the ANOVA to see if there's a statistically significant difference. So to run the ANOVA, I'm going to go to Data, Data Analysis, ANOVA Single Factor. And then I'll select my data once again. And I do have labels in the first row. I'd strongly encourage you to go ahead and highlight your labels, just because then on your output Excel labels it and it's much easier. For my output range, I'll do it in E18. And that's it. Click OK. Okay, first thing I always do when I check out an ANOVA output is I look at my count to make sure I know Excel pulled in all my cases. Oftentimes if the data isn't formatted right, or if you don't highlight the right range, it won't have the correct number here, and you'll know you'll need to go back and double check. But I have 105 cattle for each breed, that's good. The next thing I check is my p-value. Right here you see it says 2.67 or 2.76 E negative 07. That means we need to move our decimal place 7 spots to the left. So it'd be 0.00000 and a number of zeros to 76, which means it's much less than 0.05, so we did get statistical significance. So that means that somewhere in our data set, some of the 2 breeds are statistically different. But what ANOVA doesn't tell us, it doesn't tell us where that difference is. So we need to do post-hoc tests to see where the difference is. Now we have a bunch of different options for post-hoc tests. The one we're going to do most normally in this type of research is we're just going to run t-tests between our pairs of data. So we're going to compare Angus to Charolais, Charolais to Hereford, and Hereford to Angus, and see which one comes up statistically significant. But the one caveat here is that we can't use our normal 0.05 p-value. I like to explain it like this. If you have a herd of sheep and you test them for some disease, XYZ disease, you have a given chance of getting a false positive. there's a chance that you'll come up with a false positive. But if you run that same set of sheep through the same set of sheets again and do the same test on those sheep again, you increase that chance of getting a false positive. The same thing happens if we keep rerunning and rerunning and rerunning the same data set. We increase our chances of getting a false positive answer. So to address that, we run what we call a Bone-Ferroni correction factor. And this is described in the notes for the week, but simply it's just dividing our p-value, which is 0.05. We divide that by the number of tests we want to run. So if we want to run all the comparisons for this group, we'll run Angus versus Charlet, there's 1. Charlet versus Hereford, there's 2. And then Hereford versus Angus, there's 3. So if we take 0.05 divided by 3, excuse me, we get 0.01667. So in our t-test, we need to be, for p-value, we need to be 0.01667.